In this question, we are told that there is a cheetah starting from rest. I know this is the best cheetah that I can draw, okay? I tried. And eventually, it'll reach a running speed of 30 meters per second. So we can imagine that we have taken two photos. Photo 1 is while it's at rest, and photo 2 is when it has reached 30 meters per second. Next, we need to set origin and axes. I'm going to put the origin here, behind one of its rear feet. And I'm going to set the positive x-axis to be in this direction. Now, what was the question asking for? The question was asking for the acceleration of the cheetah. So let's start off by writing out our table. The acceleration of the cheetah is the unknown. But there are three things that are known in this question. We were told that the cheetah accelerates from rest. Whenever you see the words from rest, that means that the velocity in one of these pictures is 0. In this case, photo 1, its initial velocity was 0. Its final velocity, we were told it reaches a velocity of 30 meters per second, which we could write like this. And we were told that it takes 7 seconds to do so. We know the two velocities and the time, and we're looking for an acceleration. There is only one equation that weaves together these four quantities, and that's toolbox equation 1. So substitute what we know and solve. So A is equal to 30 divided by 7, which works out to 4.29 meters per second squared. In this question, we were given a gun, and we were told that a bullet would be accelerated within it. Let's take photo 1 as being before the bullet has started moving, and photo 2 just as the bullet is leaving the muzzle. Where the back of the bullet is in photo 1, I will set that as being my origin. But by the way, it doesn't really matter where you set the origin when you solve the question. I'm just solving it, or I'm just setting my origin where I think makes most sense for me. If you set it somewhere else, that's perfectly fine. You'll still get the same answer. So the origin is at the back of this bullet, and I will set rightwards as being positive. Now let's create our table. Now in this question, we were being asked to find the muzzle velocity of the bullet, that is, the velocity as it leaves the gun. That's photo 2. That's the final velocity. What were we told? It was implied that the bullet will start from rest. And we were more directly told that the acceleration of the bullet is 6.2 times 10 to the power of 5 I hat meters per second squared. And the time that it takes for the bullet to get accelerated was 8.1 10 to the negative 4 seconds. So we have two velocities an acceleration, and a time. There's only one equation that weaves together these four quantities, and that's toolbox equation 1. So the acceleration is 6.2 times 10 to the power of 5. The time is 8.1 times 10 to the power of negative 4 is equal to the v final, which we don't yet know, minus v initial, which is 0. So all we have to do is multiply 6.2 10 to the power of 5 by 8.1 10 to the minus 4. Let's go ahead and do that. 6.2 times 10 to the power of 5 multiplied by 8.1 times 10 to the power of negative 4 gives us 502.2 meters per second. This next question is a tad more complicated, and that's because we have two different types of motion taking place. One as the train is accelerating, speeding up, and one as it's experiencing a negative acceleration, that is, slowing down. Let's take a look at part A, the place where it is speeding up. So we start off by drawing our picture. I know they said a freight train, I only know how to draw a steam train. And we're told that the steam train is speeding up over time. So, photo 1 is going to correspond to where we had its initial velocity. We were told it was moving at 4 meters a second. And photo 2 will be after it has accelerated somewhat. I'm going to set my origin at the front of the cowcatcher in photo 1, and I will set rightwards as being positive. What information is known and what information is unknown? We were told that the initial velocity of the train was 4 I hat meters per second. We want to know its velocity after it has accelerated, so that means that the final velocity is the unknown. The acceleration is 0.05 I hat meters per second squared. The time was given as 8 minutes, but you have to be careful. Everything else is in seconds, so we have to convert this into seconds as well. There's 60 seconds in a minute, so 8 minutes is the same thing as 480 seconds. And later on, part C is going to ask for the displacement. So first we need to solve for the final velocity, and later on we will solve for the displacement. So we're given initial velocity, acceleration, time, we're looking for the final velocity. Toolbox equation 1 is the only one to weave those quantities together. So, acceleration, 0.05, time, 480, is equal to v final, which is unknown, minus 4. 0.05 times 480 gives us 24. So 24 is equal to v final minus 4. Therefore, v final is equal to 28 I hat meters per second. In part C, you were asked for the displacement. At this point, you now have v initial, v final, acceleration, and time. You have so much information that you could use any of the other toolbox equations to solve for delta x. I'm going to go with number 3, since it hasn't gotten much love recently. Now, let's plug in all the information that we know. The time is 480, is equal to V initial, 4, plus V final, 28, all divided by 2. 4 plus 28 gives us 32, divided by 2 gives us 16. So we now have delta x over 480 is equal to 16. So delta x is equal to 16 times 480, which is equal to 7,680. 7,680 I hat meters. Part B is subtly different from Part A. And the reason why is because you don't have the same acceleration in Part A as you do in Part B. So, from the perspective of kinematics, Part B is basically a totally independent question, which is why, rightly speaking, I ought to make this question out of 2 points rather than out of 1. Here, in Part B, the train is initially moving with the velocity that was the final velocity of Part A, that's 28 meters per second, but it gradually comes to rest, to a stop. So, this is photo 1, when it's moving at 28, and this is photo 2, just as it comes to a stop. I will set my origin to be the front of the cowcatcher, and I will set rightwards as positive. Now, we were told that the initial velocity of the train in photo 1 is 28. It comes to a stop in photo 2, so its final velocity is 0. And its acceleration was negative 0.55. We want to solve for the time, and for part C of this question, we want to solve for the displacement. Let's solve for the time first. We know initial velocity, final velocity, acceleration, we're looking for time. There's only one equation that weaves together those 4 quantities, and that's toolbox equation 1. So, acceleration, time is unknown, final velocity, 0, minus initial velocity, 28. So, we now have negative 0.55 times time is equal to negative 28. So time is equal to negative 28 divided by negative 0.55, which equals 50.90. Let's call that 50.91 seconds. And now we need to find the displacement. At this point, we have so much information, we can use any one of the other toolbox equations to solve for displacement. It's been a while since we've used toolbox equation 4, so I'll go with that. V final squared minus V initial squared equals 2 times A times delta x. So v final minus v initial, both of them have to be squared, is equal to 2 times acceleration, negative 0.55, times delta x. (28) squared is 784. So 0 minus 784 equals 2 times negative 0.55 is negative 1.1. So rearranging this a little bit, we now have negative 1.1 times delta x is equal to negative 784. I'm going to divide both sides by negative 1.1. And I end up with delta x is equal to 784 divided by 1.1. $712.7. And this would be I hat meters.